All right, I'm going to go ahead and get started, if that's all right. So thank you all for coming here. I know it's a really busy time of the semester, so glad to see some people showed up. I was afraid it'd just be me standing here, like kind of talking to no one. So this is good stuff. All right, so in this last workshop here, I'm going to be going over multivariate analyses, and I decided to focus just specifically pretty much on confirmatory factor analysis. So I did this for a couple of reasons. One is that this is a method that I'm most familiar with, so I'm most comfortable telling you guys about how to do some of this stuff in R. And another reason is I think it's a really popular method that's being used. So anytime you develop a measure, you're trying to better understand the nature of a scale, or you're interested in seeing if it is doing what it's supposed to be doing, and other things along those lines. Factor analysis is a really useful tool in that regard. So that's just another reason that I wanted to focus on this. So I have a variety of things on the agenda. So most of them, again, are primarily confirmatory factor analysis based. I'm going to refer to it as CFA throughout this since that's quicker. So we'll look at how to specify different types of CFA models. So ones that include a single latent factor, ones that include multiple latent factors, and then some higher order CFAs, and how to request different parameters for these models and different fit indices and things like that. And then we'll also look at how to identify sources of misfit with these models. So as is often the case when you have a measure or you create some sort of model of that measure, there's going to be issues with it and things that are basically contributing error and causing your model to not be a good fit for the data. So we'll talk about how to examine those sorts of things. And then I also have a lot in here with visualization of CFA models. This is something I like because I find it's not only a nice way to sort of summarize the main results, but it also helps me make sure I set up the model correctly. So it has multiple purposes. And then we'll look at how to examine group differences with CFA. So this is also called measurement invariance. And then I'll finally, depending on how much time is left, conclude with some code about how to conduct a network analysis. And this is not CFA stuff, but it's still a multivariate technique that can be used for looking at your measures. It's something I only just recently figured out how to do, so I kind of wanted to include that at the end of this as well. So I'll go ahead and get started. Again, as a reminder, these are the libraries that we're going to be needing, the packages we'll be using. So if you're following along, be sure to have those. Otherwise, feel free just to watch the screen here. So I thought it'd be interesting to use a personality data set because it's really simple to illustrate a lot of things with confirmatory factor analysis. So we're actually going to be using a data set that is currently within the psych package, the BFI, so the Big Five inventory. This is a data set that contains some items for the Big Five measures of personality. And I think it'll be really useful to look at CFA techniques with this data set. And you can use the following code to bring it up. I've already brought it up here, but this is how you would load that data set from the psych package. And then I'm going to go ahead and I'm going to opt to do a lot of copy pastes back and forth here. I tend to have lots of typos in my code when I'm typing things out, and I don't always remember some of the code here. So I'm just going to do a lot of this. What we can do is we can run it. And what this will do is it just provides a summary of the data for us. So just to kind of show you what we're looking at here, we have the 5 factors of personality. So agreeableness, conscientiousness, openness, extroversion, and neuroticism. And for each of them, we have 5 items that are representative of those different factors. And that's pretty much the majority of what is in this data set. You can see there's a couple other things, like gender, education, and age as well. But what we'll primarily be interested in is these personality items. So the first thing that I want to do is just talk about how to specify a really basic CFA model. So to do that, you can use the following code here. And this is where you're setting up your model. So I'm going to go ahead and paste this in R and have a few things to say about it. So I'm just going to call this model A. That's what I'm labeling it on the left side here. And then what I'm doing is you'll see this symbol here. This is basically saying that these items on the right-hand side are loading on to this factor that we're defining. So we're going to call this agreeableness. I'm just calling it AGR because it's a little bit shorter. So basically, what this means is we have this agreeableness factor, and we have these 5 agreeableness items loading onto that factor. I'll go ahead and run that. So there's no output yet. We're just kind of setting up our model here. So then what I'm going to do is, I'm going to use the CFA function, and this is with the Lavon package, to run the confirmatory factor analysis model that we're looking at here. So again, you have to label it. I tend to call this like fit A. So we're going to look at the fit of this first model that we're specifying. You can see here is the CFA function. Here's the name of the model that we previously defined. And then we're just telling it what data we're going to run this model on. So what we can do is we can run that. So now we have our model. Basically, at this point, all we need to do is request the parameters and information we're interested in for this model. And there are a couple ways to do that. I'm going to illustrate some of the ways you can do this. I'll only use one of these consistently throughout the rest of this. I just kind of want to show you different strategies you have here for getting information about your model. So we can summarize our model with the summary function, and then we put the fit A model that we defined previously in there. And we get the output for that. And some of the important pieces of information I'll just kind of point out here. This here is a chi-square value. So it's basically telling you what the fit of the model is. And chi-square values, you don't want them to be significant. If they're significant, that means it's a poor fitting model. But it is also driven somewhat by sample size. And this data set, there's almost 3,000 participants in it. So it's always going to be significant. So the first part, you get information about the fit of your model. And then as you go down, you get some information about the parameters of your model. So for instance, there's information about the factor loadings here under the estimate column. And at least for me, that tends to be the primary thing I'm interested in here, because it's telling you how good those items are, essentially. Factor loadings are kind of like regression weights. You know, higher values mean it's more strongly related to that latent factor. So in this case, they're all pretty high. You'll notice they're negative. I think this is happening just because the items are reverse coded. I'm not 100% sure because I don't know a ton about the data set, but I would guess that's why that's happening. Okay. An alternative way that you can get some information about your model is to use the parameter estimates function. So I'm just going to paste that in here and run it. And you get a lot of the same information, not necessarily information about the fit, but information about the factor loadings and variances. And I just want to make a note real quick and kind of interpret the output a little bit here, because when I first saw this, I was a little confused about like what's going on. So I just want to make a note that when you see this symbol, it's basically telling you it's a factor loading or sort of a regression-y like coefficient that's telling you how good of an item it is. You'll notice there's another symbol here, which is 2 of those squiggly lines. This is a covariance. And when it's a covariance between an item with itself, it's just the variance of that item. So that's essentially like what that information means. And I'll continue to refer to this as I run some more models here, just so the interpretation of this is hopefully evident. But I just wanted to make a note of that. It's also in the R markdown about how to interpret that. So this is the information we get with the parameter estimates function. And one of the things when you run these pieces of code without specifying anything else, I mean, you get really basic information, and a lot of times it's not all the information that you're after. So what you can do is you can actually add some things to the code. You can tell R, I want to request other kinds of information for this model. So I'm just going to copy paste that in here and explain quickly what's going on. So you'll notice that this is the same code as this here, where we're trying to get a summary of this model, but we're actually requesting some specific things. So we have fit measures equals true, standardized equals true. This is just us telling Lavon that we want more information about the fit of our model, and we want some standardized estimates of those parameters as well. I tend to use this like chunk of code as my default whenever I'm looking at CFA and Lavon, because I find that for the most part it provides useful information. So I'm going to go ahead and run this, and we get some additional output. So I'll just kind of take it from the top here. So you'll note that you're getting more information about the fit of your model at the top of this output here. So again, we see our chi-square value, but we're also getting some other fit indices. So without getting into this in too much detail, basically for both of these, if it's above 0.95, that indicates good fit. So I'd say based on that criteria that others have established that this is a pretty decent model. There's additional fit information that appears as well. So there's this one here called the root mean square error of approximation. And in general, below 0.08 is considered good fit. So again, we're seeing consistent evidence that this is a good fitting model. And there's additional information about the fit as well that you can explore if you're interested. So recall that we requested information about the fit of the model, but we also requested standardized parameters. And that's this information on the right-hand side here. There are two different columns, and basically they just slightly differ in how it's standardizing the information. I put it in the R markdown because I was frustrated when I was first using Lavon. I didn't understand the difference, but basically just really subtle differences in terms of how it's standardizing those parameters. It is in here somewhere. Yeah, it's in there somewhere. And you can do some other cool things. So like I mentioned, this is the basic chunk of code I use when I'm looking at CFA models, but you have lots of options in terms of the parameters you can request. So another thing you can do is you can bootstrap some of your estimates. So if you recall, we're getting estimates of standard error here. We could actually bootstrap the standard errors if we wanted. And it's as simple as telling R that we want to request that information. So that's this SE, standard error equals bootstrap. So if we ran that, yeah, this takes a little bit to run. Forgot about that. If we run that.
You're going to sing all this stuff. Yes. You have to hold your breath.
Nope, come on, run. I don't want to sing.
No, that's not what you love.
A dance
Yeah.
would be a-
A dance.
number would be lovely.
Jeez. Oh, bummer, it ran. Okay. I'll have to skip some of the other analysis there that long. No, I'm kidding. So we can summarize this in the same way that we're summarizing the previous model. You'll notice I called this fit boot, just it's a name. So if we run this, we get the sort of standard output, but one of the main differences is it's telling us our standard errors are bootstrapped, and that's the standard errors here. And if we were to compare them, I believe they'd be slightly different. So that's one way to bootstrap the standard errors of your parameters. And you can bootstrap other things. And this, I was feeling nerdy one day, and I was figuring out this thing here. You can actually also use the bootstrap Lavon function within the Lavon package to bootstrap your fit indices, which I think is really cool. And there's some articles out there on this. So I just want to quickly demonstrate how to do that. Again, just trying to illustrate here, there's lots of different kinds of output that you can get. Hello. I don't know why I did that.
I like this name better.
What's that?
I like this name better.
Boot fit? Yeah, so yeah, that part was not so clever. But yeah, so you'll name this like you did previously. You'll use this bootstrap Lavon function. And the code here is you're telling it to do certain things. So you're telling it to look at this model, draw 10 bootstrap samples. It's not a lot, but for the sake of this analysis not taking forever, I'll just do 10. And then you have this function, and then you're sort of specifying the function saying you want to get information for the fit indices. So again, just a way to illustrate that you can use the features to get all sorts of cool stuff. So it does its magic, and then we can summarize the bootstrapping of those fit indices, and voila. So there's only 10, so I checked, and these results kind of diverge from the fit indices we just looked at, but I also ran it with 100, and the results match more closely, so flexibility. But yeah, just something cool if you're ever interested in doing that. So I mentioned previously that visualizing the results of CFA models is something I like to do, so I wanted to show you all how to do that and give you the code for it. So this is with the semplot package, and you'll use a sempaths function to basically get a visualization of your CFA model. So I'm going to do that now, and I think it can also provide a lot of clarity of the model we're looking at. You get some error messages. They're not like critical things. So it's kind of hard to see. This is just the default like graph that you get. I don't even know. Can you see the lines? Yeah. Okay, so there are lines going from your latent agreeableness factor to those items, because it's basically saying that people have a certain level of agreeableness, and it causes them to respond to those items in a certain way. Now, the default image is not very helpful, but the semplot package has like a ton of different things you can add to that line of code to get a far more interesting figure. So I went ahead and put some stuff in there for us. So one of the immediate things, at least I noticed about the model, is it doesn't tell you the parameter estimates. It just visually presents what the model is. But you can actually request those parameter estimates by using this code here, what equals est. So it's basically saying we want to include the parameter estimates in this model. And I won't go over this other stuff in too much detail, just suffice to say that these additional pieces of code that I added to this sempaths function are ways that you can manipulate the visualization that you're getting. Some of them make the lines thicker. Some of them change the color of your model. You can change the size of the observed variables or the size of your latent factor and so forth. You can also change like the rotation of it as well. So I'll illustrate some of this. I think it'll be clear once I run it. So when we use that set of code, we get, at least in theory, a little bit better looking model. So you can see the parameter estimates have been added. And if we went back and looked at the output that we had previously, we would see that this information, of course, matches exactly. It's just taking that information and putting it in a visualization of the model. So information about the factor loadings, we have our observed items here and those variances. We have our latent factor and the variance associated with that. So like I mentioned, I also like to use this stuff just to verify that the model I am running is correct. And in this case, like everything's set up well, you're getting results that you would expect. And so we'll look at a different model now. So this is going to be a CFA model that contains all of the factors of personality. So I was only looking at the agreeableness one there, just to sort of illustrate some basic things. But you can actually specify a CFA model that includes information for all those 5 factors of personality. And you do this in the same way. You simply just add some lines of code that are saying, okay, we have these conscientiousness items. Those are going to load onto this conscientiousness factor. Same thing with the remaining factors of the personality. So we would create this model in the same way. So we would run that. We would then use the, okay, I'll just do both of these at once. We would use the CFA function in Lavon, so we would run that. And then, like I mentioned, this is sort of the chunk of code I like to use for the output, so we could run this and get a summary of this model. And suddenly we have a lot more output and a lot more information. So again, just to illustrate how to kind of generally interpret some of this output, we have our chi-square test here. We have other indicators of model fit here. You can see they're below that 0.95 threshold, so this actually isn't a great model. So we'll try to figure out why that's the case in a little bit. But the RMSEA I mentioned below 0.08 is generally good, so we can see from this perspective, it's an all right model. So this is something that happens a lot. And you see discrepancies in terms of the fit of your model, which certainly makes it harder to interpret it, but it happens. And then of course we have lots more parameters being estimated here. So these are like the factor loadings for those conscientiousness indicators on that conscientiousness latent factor. Same thing for extroversion, neuroticism, openness, and so forth. And then covariances are just telling you how those latent variables are related to each other. So kind of like a correlation, but not quite.
I learned today with Jim that the std.all is actually the correlation.
Oh, are you serious?
Yeah, because remember I had that question earlier.
Oh. Oh, that's really cool. So thank you for, sharing that. That's good stuff. So here's the correlation, guys. This last column here. That is true. And before they weren't. I'll have to get back to you on that one. Because, I'm not sure why that would be the case. Interestingly, there's other kinds of standardized estimates you can request specifically too. Like there's a lot of them. But yeah, it is interesting they're lining up here because I think they'd be different, but they're not. But yet the variances are. So I don't know. Good question. So yeah, lots more output. Basically, this.
Oh, it's the covariance.
Oh, what's up?
I don't know. Maybe it's because it's like covariance between. I don't know. Anyway, sorry.
No worries.
I'll just stop it.
You're fine. You're fine. So that's probably, this model here is probably like the standard model that you would look at with at least this kind of data, personality data in the big five. And of course, we can also visualize this information. Again, this might be a little hard to see because the default is not very great. I have this in the R markdown as well. It's a little clearer. And I opted not to put the parameter estimates in here because you can see this is kind of a complicated model. There's a lot of arrows. There's a lot of things going on. And I was not able to figure out how to make that look super pretty. But if you did need to create a visualization of this CFA model, this is the basic code for how to do that. And this is, if you can see, what that model kind of looks like. So you have arrows going from all your latent factors to the items for those factors. So I'll just keep plugging away at some models here to kind of illustrate some things. So you maybe have a model where you want all your items to load onto sort of one factor, like one sort of broad personality factor. Doesn't make much sense, but let's say you were in a situation where you wanted to do this. You would simply take all of your items and, you can see this is a pretty long chunk of code. But basically you're saying all these items load onto this one factor. And in the same way that you examined the fit and parameters for this model, you can do that here as well. So I'll just run these both at the same time. And you get the typical kind of output here, chi-square value.
That's great.
Yeah, so my interpretation of this would be this is an awful model, but I just wanted to illustrate how you would load on, take all these items and load them on the one factor. I would never do this, by the way. Like,
I actually did it.
oh,
But in a way to show that my concepts are different, even though they're correlated too strongly.
okay.
Another scale.
Yeah, so I think there are certain constructs and measures where doing something like this makes sense. Personality probably isn't one of them. Yeah, so for illustrative purposes, so yeah, really, really bad fit. So finally, this RMSEA value, you see it also changed. It's above 0.08. It's just really bad fit no matter how you look at it. And there's all our gross parameters. But let's say that we wanted to be certain that this was a worse model than the previous one. Oh, let me visualize it first. So just to clarify, this is the model that we just specified. 25 items for one latent factor. Yep, not pretty. Okay, so now let's say we wanted to definitively state that this model is worse than the previous one. We could do a chi-square difference test. So I've sort of pointed out that chi-square is one of the fit indices you get in the output. So strangely enough, you use this ANOVA function to run the chi-square test. And you just put the names of both of your models in there, and it'll do everything else for you. So you see chi-square difference test. Recall that lower chi-square values mean better fit. So for that initial model we ran with the 5 factors of personality, chi-square is around 4,000, but the one with only one factor is around 10,000. So it's telling us, since this is significant, that this other model is significantly worse than the previous one, much larger chi-square. Not at all surprising. So a useful way to compare models. And then I just want to talk about one last kind of model that you can look at. And again, this doesn't make much sense in the context of personality, I think, but it can illustrate at least how to do this and provide you the code with this for your own analyses. And I know Stacy's an expert on this now, so feel free to chime in.
This was an hour earlier.
I'm sorry.
Okay.
So for this example, I removed the last 2 factors of the personality traits, so neuroticism and openness. So here we have agreeableness, similar to how we specified it previously, as well as conscientiousness and extroversion. But then what we're going to do for this last line of code is say, okay, we want to specify a additional factor that is responsible or causes variation within these other factors. They call this like a higher order or hierarchical factor. So I'm going to call this personality. Again, it's kind of a lame example. Like, I think this makes far more sense with things like intelligence and motivation and other kinds of constructs. But basically what we're going to say here is that these agreeableness, conscientiousness, and extroversion latent factors that we defined previously are going to load onto this overall personality factor. So we'll run that, and I will have a visualization of this, which I think will make everything clear. But just real quick first, we can get information about this model in the same way we've been doing up to this point. So our parameters, information about the fit. So you can see it's certainly better than that one atrocious model we looked at, but still not a great fitting model. And one of the main differences is in the output. You can see here's that like overall personality factor that we created and how those latent constructs are then loading onto it. Again, it's not a great example, but I just wanted to give you the code to be able to do something like this. All right, before going on anymore, I want to visualize this because I think that'll make all of this a lot clearer. So I'm just going to use the SEMPaths function again to create a visualization of what this model looks like. So if we run it with these particular settings, we get this. So this is what we were doing. We specified this higher order personality factor that causes variation in our other factors, and then those still have the indicators loading onto them. So it's a way of sort of hierarchically setting up a confirmatory factor analysis. And it probably is worth pointing out that like there should be a good reason to do this because you can, it's just a more complicated structure. It's not parsimonious, but this is how you would look at something like this. I think intelligence is maybe a good example of when you would see this kind of structure. So if you had a measure of intelligence, you could think of this factor on the left-hand side as like general intelligence. And this causes you to have high visuospatial intelligence, reading comprehension, numerical ability, and so forth. And those different latent factors, you could use different items to be representative to test for that kind of stuff. But that's how you would set up a higher order CFA model. So like I mentioned, models often are not a good fit. They can have some issues going on with them. And it's not always clear just based on the fit indices and the parameter estimates that you get, like where that misfit is occurring. And one of the ways you can look at the fit of a model is by using modification indices. And basically this information tells you how much the chi-square value would change if you examined a particular parameter, added something to your model that you weren't currently looking at. So it's sort of exploratory. I wouldn't recommend using this and then making changes to your model just to get the best fitting model possible, because then it's losing parsimony, you're capitalizing on chance results and stuff like that. So I wouldn't recommend using it in that way, but I really like it as a way to try to better understand why your model isn't a good fit. So I'm going to demonstrate how to get that information with this modification indices function. So we're going to look at it for model B. So that's the one with the 5 factors. That's probably the most typical one that you would see with personality variables. And then I'm just going to tell it to sort those values and then just give me the top 30. So I'll run this and kind of explain what's going on. So when we run it, we get this list of things here. So we can see we're seeing symbols for covariance, symbols for factor loadings that we've kind of seen previously. We're also seeing this MI here. That's the modification index, and this is the value associated with this information on the left-hand side. So I sorted it, and basically what it's telling us is if we estimated this parameter, our model fit would improve by this much. So the chi-squared would get smaller by that much approximately, because again, smaller chi-square equals better fit. So in this case, the top one we're getting is telling you that these two items should be correlated, but it's the error variances of these items. And well, in this case, I mean, error is supposed to be random, so correlating the error variance of different items that you have it doesn't make a whole lot of sense. But for some reason, correlating information that's supposed to be random would really help our model. So you can see how this information might be used for nefarious purposes. It's oftentimes why structural equation models and factor analysis that people publish are not replicable, because they're doing things like this in the background to improve the fit of their model. It's kind of a problem. But in this case, I think this information is useful because it's telling us there's something about these two items that they're very related, the error is related. So one way of interpreting this is that these two items are redundant, so their errors are correlating. So it could be simply a matter of getting rid of one of those items. one of the other things I notice here is I see on the right-hand side a lot of like E3, E4, E5, and next to these is a factor loading symbol. So what it's telling us is, hey, you could really improve the fit of your model if you took these extroversion items and loaded them onto different latent constructs. So in this case, it's saying, take this extroversion item, load it onto the openness factor. Take this one, put it on openness, this one on conscientiousness, and you would improve the fit of your model. Of course, this is ridiculous because these should be representative of extroversion, not other constructs. So one way of maybe interpreting that information is that these are crappy items and they're not actually tapping in the extroversion because they're loading on to better, or the results are saying that you would have better fit if you loaded these onto different constructs. So just, I mean, obviously there's tons of information here, an illustration of some of the ways you can use that information to identify why the fit of your model isn't good. So if I just had this here, I'd probably say, okay, there's some redundant neuroticism items in here. There are some really poor extroversion items and so forth. So another thing that is really useful to do with CFA is looking at differences across groups and seeing if the measurement model that you specify is consistent across these different groups. And one of the most common places I think you see this is in like cross-cultural research. So people that make a scale, you know, in English in the United States are sometimes interested in whether this scale can be used in China, for instance. So it's really important to establish that the measure functions in the same way across groups because that will enable you to be confident in the comparisons that you're making. Another example of where you see this idea of examining group differences with CFA is with different races. So for instance, you might have a test, maybe it's the GRE, and you want to make sure that different races or genders are interpreting the test in different ways because that would be problematic. So what you could do is you could see if your model is consistent across these different groups. And if it is, you can be confident that any differences that exist are due to the people's like true score rather than anything about the measurement properties or the scale itself. So I wanted to demonstrate how to do that with this data. So in this example, it'll be a basic one just to kind of illustrate how to do this. I wanted to look at the very first model that we specified that was just for agreeableness and see if that model is consistent across males and females. So which would enable comparisons between these different groups. So to do so, first, one thing I'm just gonna do real quick here is when I summarized the data earlier, everything was coded as continuous, but I'm just gonna quick code gender as categorical. So we can use that as our group variable. So you can do that with this code here. We've come across this in previous R workshops. I'm just gonna run that real quick. Yeah. Okay. So when we're examining group differences, another way of putting this is we're conducting a test of measurement invariance. So we want to make sure that our measure is invariant across groups. There's no differences across groups. So if you come across, I mean, there's multiple terms for this. And there's a really useful function. I can't remember if this is in the SEM tools or Lavon package, but there's actually a function for this called measurement invariance. So kind of like before, we're going to define what this model is on the left-hand side. We're then going to use this measurement invariance function on our first model that we looked at. So as a reminder, this is the one that just looked at agreeableness. We're going to tell it what data we want to look at. We're going to specify what the group is. In this case, it'll be gender. That's what it's called in the data set, so males and females. And then here we're just saying use maximum likelihood to conduct this test. So I'm going to go ahead and run that. And I really like this function because it gives you pretty much most of the necessary information, like in a really condensed set of output, which I think is really useful. So this is the output we get here. And basically when we look at a measurement invariance, we are conducting a series of models where we are constraining things with each model we look at. So in the first model, it's often called like configural invariance, is just looking if the factor structure is consistent across groups. So we can see here the fit of this model is good. So we could probably conclude that it's the same structure across males and females for agreeableness. And then what this next step here does is it constrains the loadings, the factor loadings. So recall that items are loaded onto the latent construct. So basically what it does is it says, okay, let's constrain these to be equal across groups and see if the model is still a good fit. And it does a chi-square difference test, and because it is not significantly different from the previous model, like we can conclude here that the factor loadings are equal for the agreeableness scale across males and females. And basically, we could keep going then. So for this next step, we could constrain the intercepts in these models to be equal across groups. Now we see when we do that here, the chi-square difference test is now significant. So what this is telling us is this more constrained model, the more we're like specifying to be equal across models, it's a significantly worse model in this case when we do it. So, and then this last one here, it doesn't have much to do with the measurement instrument itself, but it does it automatically. It's just looking at differences in means across males and females for agreeableness. So you can see this even further constrained model where we say, hey, what if we look at this and say that the means are equal, the chi-square value gets higher, and the significance test is, it's the difference test is significant, which is basically telling us that this model is worse than the previous model, which already wasn't great. So what you could conclude from this is there is partial invariance across groups. So the factor structure is similar. The factor loadings are equivalent for males and females with this agreeableness scale, but the intercepts are not equivalent and the means aren't. So I'd be fairly confident that you could make comparisons in males and females agreeableness based on this information, but sort of tentatively based on the results of this test. And then you get some other information down here about some of the other fit measures. So CFI, recall we want that to be above 0.95. RMSEA, we want that to be below 0.08. So we can see as we add additional constraints, this information tells a similar story. Fit gets worse, regardless of which fit index you're looking at. So that's one way to do this. There are other ways as well where you can get a lot more information, but I think it's also a little more complicated. I'll just kind of quickly show you what that would look like. So another way you could look at group differences with your CFA model is run a series of models where you specifically constrain certain things. So you will use the CFA function in Lavon again for this. So I'm going to call this like MI, so measurement invariance model 1. So this is sort of our baseline model. And you'll notice it's pretty similar to some of the previous code that we looked at, except we're having this group equals gender thing here, so it knows kind of what we're doing. So we could go ahead and run that, and we could summarize it. And we'll get sort of typical output that we've seen before, though it does break it down by group. So you can see group 1, group 2. So we know it did it right. And then you get like the chi-square values right here, other fit indices. So in this case, that would be our baseline model. Then recall for the next one, we want to constrain the factor loadings to be equal. So I'll show you what that would look like quick here. So use this code, and then you just add this additional line here at the end that says group equal loadings. So this is our way of telling Lavon, since we're using the CFA function, to constrain the factor loadings to be equal across groups. So we could run that. We get the output. So you can see there's a slightly higher chi-square. Fit's still pretty good overall though. And then again, it sorts it by group, and you can see it's putting these things next to the variable names. So I don't know what these stand for, but these appear when you constrain things to be equal. So I think it's kind of telling you that, hey, these are those things that you constrain to be equal across groups, just FYI. I'm not 100% sure, but I think that's what's going on there. So then again, maybe we're interested in whether or not the intercepts are equal across groups. So again, lots of code and output here, but as far as the code is concerned, basically the only thing we're doing is adding those additional constraints. So here we see the group equal, we have the loadings in there, but we put intercepts in there now. And we could run that model. So you can see, again, you're getting this information here that, hey, intercepts were constrained to be equal across groups. And you can see there's our chi-square, so it's getting larger. We're getting poorer and poorer fit. And then I'll just run the last one real quick, which was the means. So you can see the code's just growing a little bit. We're saying, all right, let's constrain the loadings, intercepts, but also the means. We can run all of that. And this was our final model that corresponds to what we were looking at previously, even higher chi-square, a worse fitting model. I just want to run the code we originally ran again, because it kind of just reiterates and summarizes some of this information. So here's that information again. And if you were to go back and look at the output for all those models that we were just running, you would actually see the chi-square values match exactly with each model, the CFI values match, and so forth. So it's just a matter of how you want to do this and which kind of information you're interested in. I figured I'd include both of them here just so that you can all have flexibility in terms of how you do this if you ever go about looking at invariants. So that's how you'd go about looking at group differences with CFA. So that brings me to the last thing I have here, and full disclosure, this isn't something I know a whole lot about. I only recently started playing around with this the past couple weeks. I thought it was really cool. So what I wanted to do is include this at the end of the R markdown for you in case anyone's interested in looking at network analysis kinds of things. So basically it's a multivariate technique, and it isn't like factor analysis because it doesn't really talk about latent variables at all. So if you recall with factor analysis, we've been talking about how there's this agreeableness construct that supposedly causes variation in these agreeableness items. And that's how you can account for the variance within those items. Well, with a network analysis, they basically say you can account for the variance within the items by just looking at those items. You don't actually have to invoke latent constructs. So it's kind of an interesting alternative to CFA in certain ways that can provide some useful information, I think, about your measures. So with the example I want to look at here is a correlational network analysis. So basically, it's just taking the correlation table for those items we have for personality, and it's going to conduct a network analysis on it. So let me just put the code in here and show you quick what's happening. So for this first line of code here, I'm just conducting a correlation between those 25 personality items for each of the 5 factors because I want to use that correlational information to conduct the network analysis. So I will click do that. And with the network analysis, this uses the QGraph package. So it's going to actually graph out our network of items. And I hope this will make sense once I do that because it's kind of cryptic at this point. But with this code here, I'm just telling it, okay, I want to use this particular layout, only include correlations greater than 0.1. And these are the variables based on what I defined previously. So 5 items for agreeableness, 5 items for conscientiousness, and so forth. So if I run this, we get a really cool image. So the lines are kind of hard to see, but this is the network. So it actually codes the factors into the same color. You'll notice they're all connected by lines. Thicker lines are indicative of stronger correlations. So green lines are positive correlations, red lines are negative correlations. And this is basically summarizing a correlational table in a little bit more of an interesting way, and you can actually get certain parameters based on this information. So one thing that strikes me here is how you see strong relations between, like, I guess these are the neuroticism items. So, you know, thick green lines, some of these other ones too. But then you look at these purple ones, which are openness. Like they're not strongly related to each other. They don't appear to be related to each other some of the time, actually. So again, all this information could technically be derived from a correlational table, but this is, I think, a much more insightful way of looking at that. And it can be really useful with multi-dimensional constructs when you're interested in how items within a factor are related to each other. So like this set of items here, and also how they're related to other items for that measure. And then there are some like parameters that you can get based on this information. I won't get into it in too much detail just because we have a couple minutes left, but you could run this. And with network analysis, there's this whole idea of like centrality. So basically you're getting information about how many items are connected to certain items, if the connections between certain items are dependent on other items. So I apologize, I don't know a whole lot about these parameters. I do have some resources at the end of the R Markdown that has a lot more detail about this. But again, I just wanted to include this here because I think it provides a alternative to CFA that can be really useful to better understanding your measures. So here are those resources. So I put a bunch of stuff down here that I found helpful, like all sorts of different things related to factor analysis primarily, like how the bootstrap fit indices, like what your sample size should be. I have some stuff for like the different packages that I was using in case you want to use these packages, but there's code that I didn't go over that you're interested in. So this one here has a really cool tutorial on the network analysis. Bohr's booms there, so that's cool. But yeah, so hopefully that's helpful and that this workshop's been helpful. Thank you. Yeah. Yeah, they're being punny. I see that capital R there.
Zero survey.